Okay, we've talked a lot about the kinematic equations lately, and I just wanted to show you where they come from. We can derive all of the kinematic equations from a regular velocity time graph. So we know that the slope on a velocity time graph is equal to the acceleration, right? So slope is rise over run. Rise is going to be our change in velocity, and run is our change in time. So acceleration is equal to change in velocity over change in time. We know that. That's our slope. Well, now what is a change in velocity? Change in velocity is just how far we've gone from our initial velocity to our final velocity, right? So our change in velocity is equal to final velocity minus our initial velocity. So if you think about if our initial velocity is 0 and our final velocity is 5, 5 minus 0 is 5. Say if it was 3, if we started at 3 and our final velocity was 8, 8 minus 3 is still 5. Our change in velocity would still be 5. So this is equal to our change in velocity. Now we can substitute this for this, and it gives us acceleration is equal to final velocity minus initial velocity over time. And this is our first kinematic equation. Sometimes you'll see it written this way. Final velocity equals initial velocity plus acceleration times time. So these are the same equation. It's just rearranged to solve for a different variable. The second kinematic equation can be derived using geometry. If we just look at our velocity time graph, here we have our initial starting velocity here. Here's our final velocity. On a velocity time graph, the area under the line, which they just call the area under the curve in general terms, the area underneath the curve is equal to the displacement. So that's, let's just call displacement delta x for now. So delta x is equal to the area under the curve. Now we can split our graph here. So we didn't start from 0, we started at some initial velocity. We can split our graph into a rectangle and a triangle. We know that the area of a rectangle is base times height, and the area of a triangle is 1/2 base times height. So we can figure out the area of both of these. Since we're not using real numbers, it's just conceptual right now. If this goes from 0 to vi, that means this side length is vi. So we've got initial velocity, and this side length is time, whatever time you're solving for, but right now it's just t for time. So the area of the rectangle is initial velocity times time, and the area of this triangle, the area of the triangle is going to be 1/2 the base, which is time, multiplied by the height of the triangle, which in this case, it's going to be final velocity minus initial velocity. Okay, so we know the area of our triangle and the area of our rectangle. If we add these together, this should be our total area. And remember, our total area under the curve is equal to the displacement. So let's add these together. We've got initial velocity times time plus, let's go ahead and distribute the 1/2 t inside our parentheses here. Got 1/2 final velocity times time minus 1/2 initial velocity times time. We can combine like terms. So we've got an initial velocity times time minus a 1/2 initial velocity times time, so that you're subtracting a half there. So now we've got 1/2 final velocity times time plus a 1/2 initial velocity times time. We can rewrite this equation. We can factor out the 1/2 and the t to give us delta x is equal to 1/2 final velocity plus initial velocity times time. You can leave the 1/2 separate or just put it all over 2. It's the same thing. So this is our second kinematic equation, derived geometrically from the velocity time graph. Distance is equal to the final velocity plus the initial velocity over 2 times time. We can determine the third kinematic formula using the first two kinematic equations. So I'm going to need to rearrange them a little bit to make it work. So let's take the first formula and we're going to solve for final velocity. We've got final velocity is equal to the initial velocity plus acceleration times time. And now we need to take this one and I just need to divide by t on both sides. So we got distance over time is equal to final velocity plus initial velocity over 2. Now what I want to do, I know that final velocity is equal to the initial velocity plus at. So what I'm going to do is I'm going to take this term and substitute it for this term. So let's rewrite it. Got distance over time is equal to, remember we're substituting this term for final velocity, initial velocity plus acceleration times time, so that's our VF, plus VI again, and all this is over 2. Now I can separate these terms so that they're by themselves. Distance over time is equal to initial velocity over 2 plus acceleration times time over 2 plus initial velocity again over 2. So this is the same thing, just looks different. Now I can add these terms together. So this is 1/2 VI plus 1/2 VI gives you a whole initial velocity. We've got distance over time is equal to VI plus AT over 2. Now I want to multiply both sides by t, and that gives you distance is equal to initial velocity times time plus AT squared over 2. And this is equation number 3. Distance is equal to the initial velocity times time plus acceleration times time squared divided by 2. Okay, to get the fourth kinematic formula, we again can use the first and the second one to find out the fourth one. So last time we had to solve for final velocity. This time we want to solve for time on our first kinematic equation. So that gives us time is equal to final velocity minus initial velocity over acceleration. And now we can take this term and substitute this term for time in our second equation. So that gives us distance is equal to final velocity plus initial velocity over 2 times multiplied by this whole term here. Because we're substituting this term, which is equal to time, for this term, for time right here. Final velocity minus initial velocity over acceleration. Now if we multiply, we get final velocity squared minus the initial velocity squared over 2a. And now to get the fourth kinematic equation, we're going to solve for final velocity squared. And that's going to give us final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance, or displacement. That is our last kinematic equation. Remember, d stands for distance or displacement, and that can also be delta x or delta y. And that is how we derive all 4 kinematic equations. Thanks for tuning in.